I'll do an introduction here. Chris is the managing director at Normec OWS. In 2020, when OWS decided to reopen the testing lab in Dayton, Ohio, he traveled to Belgium to learn the company and returned to the US to open up the lab with the former general manager. The lab was originally focused solely on testing biodegradability in compost, but has since expanded to test biodegradation in soil, disintegration under home composting conditions, disintegration under simulated industrial composting conditions, developed a field-scale home compostable assessment for certified home compostable products, and will soon expand to offer ISO 16929 and ecotoxicity testing. He's got a bachelor's and master's in microbiology from the Ohio State University and has worked for the U.S. Geological Survey and the Air Force Research Lab. His work includes research support to many projects dealing with surface and groundwater throughout the US and investigations on the degradation of various polymers by bacterial and fungal isolates. He lives in Dayton with his wife and daughter and 3 dogs. Thanks, Chris. The floor is yours.
All right, thank you very much. You can see my slides okay here?
Yes.
Okay, great. So thank you very much for that introduction. I'm going to go into a little bit more of the laboratory testing. So thank you very much, Margaret, for giving that brief overview of everything. And we're going to get right into this. So really, when we think about the BPI compostable logo, we really want to talk more about what's behind the actual logo in terms of the work that's performed in the laboratory to make these certified products. And for us, it really comes down to 2 broad categories. We look at the degradation aspect and also the environmental safety component of these products. And to address both of those questions, 4 key tests are performed in the lab, as Margaret mentioned. We have a biodegradation test, the disintegration test, the ecotoxicity test, as well as measuring those regulated elements in these finished items. So the first most straightforward test to discuss is the regulated elements. So for us in the lab, we take the finished item or raw resin or whatever material is seeking that certification. The material is digested using a microwave digestion method. It's run through spectrophotometry, where all of the regulated heavy metals and fluorine are analyzed and the concentrations are determined. Brief table here just showing the regional differences across from a few regions of the world, different levels of regulated metals that are set for Europe, the US, and Canada. And here in Normec OWS, we actually will measure the amount of heavy metals in a raw material, and we can do some calculations to determine that maximum concentration that an item can be used in a finished product in order to be below these threshold levels. Typically, when we're looking at the heavy metals content, we're dealing with pigments and products that have coloration in them. That's generally speaking where the heavy metals content comes from in these items. Along with this material characteristics, we also perform FTIR analysis, so we can validate that chemical fingerprint of all of the materials, and that allows for traceability over time. It allows for routine screening of those products to ensure that the chemical composition of that product hasn't changed over time during that manufacturing process. The second part of this associated with environmental safety is the ecotoxicity portion. And really, you can assess ecotoxicity by 2 means. BPI requires the toxicity test be performed with 2 different plant species. Other regions of the world also consider earthworms. Again, similar to the plant species, you expose the earthworms to compost that's created with a test item, and you look for a negative effect on those earthworms. And really, the compost that's created during this process cannot do any harm at all to any living organisms. And that's a very important point. So we always compare these to control materials, which is compost that's produced with, in the absence of a test material, and we look at the difference in performance of that compost. What I really want to highlight here is the stringency of this testing. When we make compost for ecotoxicity, we do that with a 10% input concentration of the test material, which is a very high concentration. And to give a quick example of that, using a coffee capsule example, a typical coffee capsule weighs about 1.5 grams on dry weight basis. in order to make compost at a 10% input concentration, that requires the addition of over 5,000 coffee capsules be added into 80 kilograms of bio-waste, which is equivalent to about 30 capsules per day per person of coffee. That's a tremendous amount of coffee for any individual to actually consume and then put all of those capsules into a composting environment. So it's a very high input concentration. Visually, this is what a 10% input concentration looks like. So the picture on the left here shows 1.1 kilograms of test material added into 11 kilograms of fresh bio-waste. And you can see from this picture, this is well exceeding a typical concentration of material that would exist in a real commercial composting facility. And the point that I'm trying to make in all of this is that the laboratory testing stringency is much greater than those conditions that actually exist in real-world commercial composting facilities. So now we'll get into the degradation aspect of things. And the first point that we're going to talk about is the biodegradation. And for us, biodegradation, the definition of biodegradation for BPI certification and to be in line with ASTM D6400 and ASTM D5338 is the conversion of organic carbon to carbon dioxide. There's lots of other measurements and ways to assess biodegradation, but for our purposes and the work that we do, that's the definition that we work off of. And again, to show a visual, to show that, again, the stringency of the laboratory testing. This is a typical test setup for us in the laboratory where we take 1.2 kilograms of compost inoculum, the fine fraction or the fraction that's less than 5 millimeters in particle size, plus 80 grams of test material. And this is an example of the mixture that you obtain that's actually used in the biodegradation test. So again, similar to the compost production for ecotoxicity, it's a very high input concentration that's being evaluated on the laboratory side of things. As Margaret mentioned, the pass level for commercial compostability is biodegradation of 90% within 180 days. What this means is 90% of that organic carbon present in the test substrate has been converted to carbon dioxide within that 180 days. And we want to point out that the stringency in the criteria for certification is actually stricter than nature. So here's some other examples of some natural materials that would, of course, also be added to a commercial composting facility. Things like wood fibers only degrading 71% in 728 days, all the way down to pine needles, which only degrade by about 52% in 1 year. So the actual criteria for biodegradation as set forth in ASTM D6400 and also the BPI certification scheme is actually much stricter than nature. So we get this question a lot, and that's why is it 90% biodegradation and not 100% biodegradation? And to answer that question, we really have to consider the biochemical pathway by which biodegradation is occurring. So in very simple terms, the carbon that's present in the substrate or polymer of interest in the presence of oxygen gets converted to carbon dioxide, water, residual carbon, and biomass. That residual carbon can be intermediate degradation products, and the carbon also goes to biomass growth. Again, if you put this amount of material into compost, the microbes that are present, the bacteria and fungi that are present in that compost inoculum, will also be using that as a food source to grow and multiply and divide. So in short, not all of the carbon in the polymer can be expected to be converted to carbon dioxide, but through the course of this testing, we can be confident that that remaining 10% would be non-persistent microparticles, degradation byproducts or intermediate degradation products, and biomass. And so that's why we focus on a 90% criteria and not a 100% criteria. Again, to show the increasing stringency as these standards have developed over time. In the early 2000s, the first standard, which was EN 13432, just set a flat 90% pass level for that biodegradation aspect. In the 2010s, standards were updated to reflect the requirement that any ingredients present in a finished item in a concentration of 1 to 10% needed to be tested separately for biodegradability. And the reason for that is you didn't want to have a material that was made of 90% biodegradable product, but 10% something that was completely not biodegradable, which could contribute significantly to microplastics accumulation and just in general not be biodegradable. The ingredients that were less than 1% concentration were exempt from testing, but the sum of those ingredients needed to be less than 5% in total in the finished item. If we fast forward to today, we are now considering, or it is going to be changed, I believe in 2026, to a new criteria, which is that ingredients present in a concentration of 1 to 15% will need to be tested individually. And again, the sum of those ingredients less than 1% will decrease to be no more than 3%. So again, just reflecting the increasing stringency over time of these laboratory tests. And then the last test is our disintegration test. Unlike biodegradation, disintegration is the physical falling apart of this material in compost. So now we're not looking at the conversion of organic carbon to carbon dioxide. We are looking at the physical falling apart of this material in compost. We do this under pilot scale composting conditions, ISO 16929, or the smaller version, which is simulated composting conditions under ISO 20200. This has an input concentration of 1%. The compost is incubated for 84 days or 12 weeks. And at the end of that period, all of the contents of the compost is sieved over 2 millimeters, and the entire contents is sorted through, and individual pieces of material are looked for. Again, pass criteria, 90% of that material must pass through a 2 millimeter sieve within 12 weeks, with two bullet points here that are worth commenting on: colored particles and also insufficiently degraded components. So those very brightly colored items with a lot of coloration in them, even if all of the material passes through that 2 millimeter sieve, but you can still see a lot of brightly colored item in that fine fraction, that's still going to be an issue for certification, because we don't want to see that in the finished compost. Similarly, for insufficiently disintegrated components, if you can, even if a material has reached the 90% mark, but you can still identify a discrete component of an item that has not disintegrated, that will also represent a problem for certification. A couple examples on that would be the vacuum seals on coffee bags, or we also had an example of coffee capsules where the rim of the coffee capsule remained after the 84 weeks. All the rims of the coffee capsules remained, even though the material had reached that 90% disintegration mark. And again, to show that comparison with nature, nature needs time as well. So these are two pictures of some straw, again, something that would always be incorporated into compost, and an ear of corn. And this is what they achieved in commercial composting after just 8 weeks of composting. So again, we just don't want to set the precedent that these materials will disintegrate within 4 weeks of being added to commercial composting. These processes all take time. And finally, just to quickly touch on the lab testing versus the field testing. What does laboratory testing get you? It really is a proof of an inherent characteristic. Proof of biodegradability and disintegration, has high accuracy and reproducibility, where the test material is truly the only variable and all other conditions of the test have been fixed. It allows for comparisons over time, comparison between items, and it's really the gold standard for certification and for validating claims. By contrast, field testing, which Emily is going to talk more about, really gives the legitimacy to that laboratory testing. So that's taking that product, putting it in real world conditions, whether it's commercial or home composting conditions, to evaluate the performance of that material. And with that, our contact information for Normec OWS is on this slide. Feel free to get in touch with us for any additional questions. And with that, I will hand things over to Emily.
Thanks, Chris. Have some background noise. Can you hear me okay?
Yeah.
Yeah.
Background noise. Okay, perfect. Well, thanks so much, Chris. Now we have Emily.